This is lecture 6 in my series of statistics for nuclear medicine, and I'm going to be talking about non-parametric tests. Non-parametric tests are useful because they don't make any specific assumptions about the shape of the underlying distribution of the data that we're looking at. That's why they're sometimes called distribution-free tests rather than non-parametric tests, but it means the same thing. If we're dealing with this sort of data, it's not useful to quote means or standard deviations because those rely on particular distributions. So generally the median is a more useful measure than the mean when we're talking about non-parametric tests, and range and interquartile range are more useful than the standard deviation. In the last lecture we talked about parametric tests, so we have to understand when we should use parametric tests and when we should use non-parametric tests. In order to use parametric tests, we've got to be able to calculate parameters like the mean and the standard deviation. Therefore the data must be quantitative. It must be numbers that we can calculate with. And for most parametric tests, the data should be at least roughly normally distributed. However, for non-parametric tests we don't need those requirements. We don't need to calculate any parameters at all, so it can be used with any type of data. The data can be categorical, split into categories, and it doesn't matter whether those categories are ordinal, can be arranged in increasing order, or nominal, just numbers. We can also use non-parametric tests for quantitative data, even if it's not normally distributed, because parametric tests require quantitative data that are not normally distributed, so one reason for using a non-parametric test might be that the data are not normally distributed. Of course, if we've got quantitative data that are normally distributed, we can use the parametric tests, but there's nothing to stop us using a non-parametric test as well. But generally speaking, parametric tests are more powerful than non-parametric ones, so if we have quantitative data that are normally distributed, it would be better to use a parametric test. Non-parametric tests can be performed in various ways. There are several tests that use ranking. To use ranking, you've got to be able to arrange the measurements in order. It can therefore apply to quantitative data, numbers that can be put into order, or to ordinal data, categories that can be ordered. But you can't use it for nominal data, quantities like red and green and blue, which can't be put into order. For ranking, the absolute value doesn't matter. It's only the value relative to other measurements. In other words, is this number bigger or smaller than the others? It doesn't matter how much bigger or how much smaller. And also for ranking, the direction doesn't matter. It doesn't matter whether we rank things in increasing or in decreasing order. Some examples of things that can be ranked would be quantitative data like the numbers -2.0, 0.0, 1.3, 1.4, 12.9, which are numbers arranged in increasing order. Or again, numbers like 2, 5, 5, 8, 10, 10, 12, which are whole numbers arranged in increasing order with some ties. There are 2 lots of 5 and 3 lots of 10, for example. Or ordinal data, categories like tall, medium or short, which can be arranged into increasing order. Although in that case that's not very good categories because there would generally be too many ties. There would be several quantities in the tall, medium or short group. Ordinal data like tallest, second tallest, third tallest, etc. Is good because we have them arranged in order, but we don't actually need to know the absolute size as long as we can put them in order, and there shouldn't be too many ties. This is an illustration of ranking based on heights. Here we've got a collection of men and women of varying heights, and at the moment they're arranged in no particular height order. But if we ask them to sort themselves into height order, they're now rearranging themselves so that we've got the shortest on the left, moving through to the tallest on the right. So they're ranked in order of height. And if we give them their rank numbers, 1, 2, 3, 4, 5 for the shortest, moving through 6, 7, 8, 9, 10 for the tallest, then we can see in this instance all the women have got the smaller ranks, 1, 2, 3, 4, 5 and 6, while the men have got the larger ranks, 7, 8, 9 and 10. So in this example, the ranking has sorted them into two groups of men and women. In order to rank things, this are what we have to go through. First of all, we take the n measurements in order, doesn't matter whether that's increasing or decreasing, and then we allocate ranks 1 to n for each measurement. So they're numbered in increasing or decreasing order, 1, 2, 3, 4, etc. Then we have to look out for ties, where there are two or more measurements that are equal. If that happens, we give each member of the tie the average rank of the tie, and I'll show you how we deal with that. Here's an example of some measurements: 5, 12, 5, 10, 8, 2, 10, 10. Those are in random order at the moment, so the first thing we have to do is to arrange those in increasing order. The smallest number is 2, followed by 5, and then another 5, 8, 10, 10, 12. So those are the same numbers, same measurements, arranged into increasing order. Then we give those ranks 1, 2, 3, 4, 5, 6, 7, 8. So the value 2 is ranked 1, the value 5 is ranked 2, and there's another 5 which is ranked 3. That shows that we've got a tie at the number 5 occurs twice at ranks 2 and 3. So we adjust the ranks, and instead of giving one a rank of 2 and the other a rank of 3, we give them both equal ranks. 2 and 3, the average value is 2.5, so they're each ranked 2.5. Don't worry that a half comes into this ranking, it all works out in the end. We also notice we've got a tie here. There are 3 values of 10 which tie the ranks 5, 6 and 7. So once again we deal with that by giving them all the average rank of 6. We'll see examples of how that can be applied in practice shortly. There are several tests based on ranking that we'll look at. If we want to compare a sample and a population with a known mean, then there is a test called Wilcoxon's signed rank test, which I'll talk about in part 2 of this lecture. If we want to compare two paired samples, then we have Wilcoxon's matched pairs signed rank test, which I'll talk about in part 3. And then for comparing two unpaired samples, we have Wilcoxon's two-sample rank test, or an equivalent, the Mann-Whitney U test, which I'll talk about in part 4. Another way of dealing with non-parametric data is to use proportion. This uses tests based on the proportion of the results in each category. So the data only needs to be categorical. It doesn't matter whether it's ordinal or nominal, whether it can be arranged into order or not. You can also apply these tests to quantitative data by splitting them into ranges. So for example, making one category for everything from 10 to 20, another category from 21 to 30, and so on. But generally, if you've got quantitative data, it's better not to have to do this. All you have to do is to record the number of observations, that is the observed frequency in each category, and then we use the null hypothesis to calculate how many we expect, the expected frequency in that category. And then we have ways of comparing the observed and the expected frequencies to see whether they're significantly different. Tests that come into that category of looking at proportion: for comparing a single sample with a known proportion, we have the binomial test and the chi-squared test, which I'll talk about in part 5 of this lecture. And for comparing two unpaired samples, there is Pearson's chi-squared test and Fisher's exact test, which I'll talk about in parts 6 and 7. So that's the end of the first part of this lecture, in which I've introduced you to non-parametric statistics. In the remaining parts, we'll look at the individual tests in more detail.